Hello guys, welcome back to my channels. So today's video I am going to discuss about second law of thermodynamics. So in this video I will cover the all details things uh, that is uh, spontaneous process and cyclic process, Carnot cycle and all those things and efficiency of engines and last entropy. S- and I will end this lecture with taking some example. So before we start second law of thermodynamics, first I'd like to give some introduction about first law of thermodynamics. So what is needs of second law of thermodynamics? So in first law of thermodynamics, the here talks about the energy conservation. That is, energy cannot be created or destroyed, only transform from one form to another form. And I have discussed the key points in first law of thermodynamics. If you remember, in this second law of thermodynamics, I will discuss the those points who are not tells in first law of thermodynamics. So in this second law of thermodynamics, I will discuss the limitations, what is limitation of first law of thermodynamics, and needs, what is needs of second law of thermodynamics. So let's start. So first law of thermodynamics is tells about the relation relation between heat absorbed and work performed by the system. But it does not tell the it does not put the restriction on the direction of flow of heat. They didn't tell about the direction in first law of thermodynamics. And another limitation was the first law of thermodynamics. The first law of thermodynamics says that energy of an isolated system remains constant, but it does not tell a specific change or process including chemical reaction can occur spontaneous. They didn't tell about the spontaneous process. First law of thermodynamics is saying that energy can be converted into an equivalent amount of another form. But in second law of thermodynamics, what we will discuss, the it does not tell that energy cannot be completely converted into equivalent amount of work. First law of thermodynamics saying that energy can be converted into an equivalent amount of another form, but it cannot uh, not be completely converted into equivalent amount of work. Therefore, it needed second law of thermodynamics. So second law of thermodynamics determine the direction in which energy can be transferred. Here tells about the direction and also it predict the process or chemical reaction that can occur spontaneous. It also introduces a new concept of entropy and also helps us to know the equilibrium condition. So before going to the process, we have to know the uh, needs of second law of thermodynamics and what was the limitation of first law of thermodynamics. So now discuss the process, that is spontaneous process. So spontaneous process is something like that water flow downhill called spontaneous process. If one end of rod heat flow is spontaneous to another end, heat flow is spontaneous from hot reservoir to cold reservoir. These are the spontaneous or irreversible process. So now discuss the cyclic process. So cyclic process is something when a system, after completing a series of change and return to the original states, known as cyclic process. In cyclic process, the internal energy of the system depends only upon the states. It follows the cyclic process that net change of internal energy is zero. For cyclic process, the net change of internal energy is zero. That is du is equal to zero. Therefore, according to first law of thermodynamics, du is equal to q plus w. If we put internal energy zero, then work will be negative. So here is the note points. If a series of change in a cycle are conducted at constant temperature, the cycle is said to be an isothermal cycle. If changes are carried out reversible, the cycle is said to be reversible. These are the notes points regarding cyclic process. Now discuss the Carnot cycle. What is Carnot cycle? It is employed a reversible cycle to demonstrate a maximum convertible of heat into work. It tells about the reversible cycle to demonstrate the maximum convertible of heat into work. Here there are four strokes. First is isothermal, second is adiabatic expansion. Isothermal, first one is isothermal expansion, second is uh, adiabatic expansion, and third one is isothermal compression, and fourth one is adiabatic compression. So one by one I will discuss. Okay. So here, as you can see in right sides, the pictures of Carnot cycle is drawn. So x-axis is the volume of gas and P is the pressures. So first step A to B, second B to C, third C to D, and last one D to A. So all these four process I will discuss here. So first one, isothermal. So isothermal expansion, we are talking about gas, instance of gas. So gas here, isothermal expansion means gas here expanded. That's why the volume is increases from V1 to V2. As you can see here, in x-axis the volume and y-axis the pressure. So volume is increases in isothermal expansion. Therefore, the for ideal gas, the internal energy will be zero. According to first law of thermodynamics, because here temperature is constant, That's why internal energy will be zero. According to first law of thermodynamics, if you put internal energy zero, the work is negative. Okay. So what it indicates that heat absorbed is equal to the work done by the system on the surrounding. That's why work is negative. Let's talk about the in details of calculate the work. So let's Q2 is the heat absorbed by the system at temperature T2 and W1 is the work done by the system on surrounding. Therefore work is Q2 is equal to minus W1 RT2 ln V2 by V1. So this is the expression of work that has been done by isothermal expansion. Now talk about the second one, adiabatic expansion. So here if you see second process, this one. So first one isothermal expansion, that is volume is being increases from V1 to V2, and second one is uh, this is adiabatic expansion. Volume is also increases from V2 to V3. Okay, BC process. So here adiabatic expansion volume increases from V2 to V3 and temperature is decreases T2 to T1. So because of adiabatic process, the heat will be zero. So according to first law of thermodynamics, D is equal to Q plus W. If you put the value of Q, then du you will get internal energy, change in internal energy for state process is equal to work done. Here the process is expansion, therefore work will be negative. So by convention, the work is negative. So by definition, Cv is equal to du by dt at constant V, and if you simplify this expression, du is equal to Cv into dt. So here the volume temperature is decreasing, so T1 minus T2, work is negative, so minus W2. If you consider W2 for second process, work is denoted W2. So Cv T1 minus T2, and if we simplify this, so this plus sign will cancel out because T1 will T2 will come before and T1 comes later. So you will get this work equation for the adiabatic expansion. Okay. Now third one is isothermal compression. So if you see the process, so this one isothermal compression. So here volume is decreasing. Okay, volume is decreasing V2 to V4. So as you can see this x-axis, so volume is increasing left to right, but the process is going from C to D. So volume is decreasing. So for this isothermal compression, the reversible and isothermal compression at lower temperature T1. So volume is as decreasing and temperature is lower, that's why internal energy will be zero. So work, so heat Q minus Q1 is equal to W3 for third process. W3 work is your denoted. So RT1 ln V4 by V3. So V4 is lower than V3. So V3 is higher volume and V4 is lower value. Okay, so this is the W3 for isothermal compression. Now last one, fourth, adiabatic compression. So for here the uh, gas is restored to the its original state from D to A, as you can see here, D to A, fourth process. So here the pressure is increasing, P4 to P1. Pressure is here increasing and volume is also decreasing. So here you will get the relations. Gas is compressed adiabatically. In this case, the work is done on the system. Hence, W will be positive. Okay. According to first law of thermodynamics, this since adiabatic process Q is equal to 0, if we put all these value here, so W will be positive. Du is equal to Cv dt Cv and T2 minus T1. So we'll get work for this adiabatic compression. Now discuss the efficiency of heat engines. What is efficiency of heat engine? Actually, it is the fraction of heat absorbed by the engine which it can convert into work that gives the efficiency of engine. As you can see, efficiency is denoted by this symbol. So efficiency is equal to W upon Q2. W is T2 minus T1 and this is equal to W upon Q2 is equal to T2 minus T1 upon T2, and this is less than the efficiency of any engine is always less than 1. As you can see here, I have mentioned in note point the efficiency of heat engines always less than 1. So no heat engine has yet been constructed that which has efficiency equal to 1 or unity. But mathematically, we can say if the temperature T1 is 0, the efficiency will be 1. If you put T1 is equal to 0, the efficiency will get 1. But um, mathematically is possible, but theoretical experimental is not possible. Okay. So efficiency actually depends on the difference between T2 minus T1. T2 and T1, if the greater the difference between temperature source and sink, then greater will be the efficiency. Okay, so net heat absorbed by the system Q is equal to Q2 minus Q1 according to first law of thermodynamics. Net work is equal to Q2 minus Q1. So this you will get this relation Q2 minus Q1 upon Q2 TO2 minus, this is relation between temperature and heat. Okay, therefore the efficiency you will get Q2 minus Q1 upon Q2, T2 minus T1 upon T1. Okay, T2. Okay, so now come to the and last points, that is entropy. That is most important. So what is entropy? Actually, entropy is a function of state. It is a state function. Okay, the change of entropy delays for change of state from A to B will invariable that can be same whether the change is reversible or not. What does it mean? Entropy is a state function. The change of entropy for change of state A to B will be invariable. Okay, are same whether the change is reversible or not. So entropy is equal to integration of A to B q dq upon d, dq heat upon T Entropy change for a finite change of state of a system at constant temperature is given here. Del S is equal to Q reversible upon T. The units of entropy is joules per degree. Okay, joules per degree Kelvin, or we can write joules Kelvin inverse. Okay, so this is all about things. Okay, now discuss the some entropy change in isothermal expansion of an ideal gas. Okay, so here we talk about the entropy change in isothermal expansion for ideal gas. Isothermal, if temperature is constant, then del U is equal to 0. Internal energy change is 0. First, from first law, you will get this. Work is negative. So Q reversible for reversible process. Q reversible is equal to minus W, and del S, if you write a entropy equation, del S equal to Q reversible by T, or del S is equal to N or T. Q reversible is equal to N or T ln V2 by V1. For expansion, the volume is increases, so V2 by V1 upon T, you will get this expression, most important expression for the entropy change of isothermal expansion of ideal gas. So now take some examples regarding this expression. So for example is 5 moles of an ideal gas is if the 5 mole of ideal gas expand reversibly from a volume is given in here 8 decimeter cube to 80 decimeter cube at temperature of 27 degrees centigrade, then here asking the um, calculate the change in entropy. So here first we will write the all those things that given in this example. So given here moles, 5 moles, numbers of moles is given 5 moles. V1 volume is 8 and V2 is 80. Temperature is given. So we have to calculate the entropy change. So as we know here the entropy change formula is nRT ln V2 by V1. So if you put here directly you will get the entropy. Okay. So this is the example regarding the entropy calculation. So now discuss the entropy change that accompanying change of phase regarding. For solid state phase to liquid phase, the del S fusion. Here the fusion process is happening, fusion. So del S fusion is equal to del H fusion upon T fusion. And second one is from liquid phase to vapor phase, del vaporization. Because here the liquid phase to vapor phase. So vaporization process is happening. So here the boiling point, TB is boiling point and fusion point, FUS fusion point. So for this case, the entropy del S vapor is equal to del H vapors upon T. Here also is heat. Now calculate the entropy change of an ideal gas that with change of P, V and T. For n mole of ideal gas at T and V variable, you will get expression like this. Del S is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1. Okay. So at earlier case, T and V was the variable. But here, if T and P is variable for n mole of ideal gas, then you will get this expression del S is equal to NCP ln T2 upon T1 minus NR. Earlier case here was the positive and from V1 V2 is replaced by P2 because P here is the variable. Earlier case V was the variable, T was the same. Earlier case here the T is also same. Okay, but here added CP. Earlier case it was CV and CV. So please check the difference between what mm, the difference, how you will get the at different variable, how you will get the different equation. Okay, last things I will discuss the entropy mixing. I will continue in next video, but uh, little about I will give some introduction entropy mixing. Entropy mixing. So it is defined as the difference between entropy of the mixture of gas and the sum of the entropies of the separate gases, each at pressure P. Thus, the equation of this mixing of entropy is equal to minus R summation of Ni ln Xi, where Ni and Xi are the numbers of moles and mole fraction. Xi is the mole fraction respectively. So total numbers of moles is equal to N1, N2 plus N3, that is, and for 1 moles of gas you will get this mixing of entropy minus or summation of Xi ln Xi, that is Xi is the mole fraction. Okay, so this is all about in this video. So I hope you understood uh, all those things. If you have any doubts, please comment on comment section. I will see. And if you found this video interesting, so please do like and comment, and thank you for watching.